We're looking at a visual model of the generation and propagation of an action potential. An action potential could be defined as an electrical spark or an electrical signal that is generated in an axon of a nerve or a neuron, which is a nerve cell, and then that is propagated sequentially down that axon to the end of the neuron, which we call the synaptic end of the synaptic knob. At this point, potentially that electrical signal can be sent on then to another nerve or a muscle or a gland. In the model that we're looking at an action potential that is generated, propagated, and then stimulates a subsequent nerve. We're going to first look at a very sensitive area, which is important for the original generation of an action potential. And this is a region that is a swollen knob region that is right at the juncture between the end of the cell body and the axon. And this is called the axon hillock. In the region of this axon hillock, there's a large population, a large number of voltage-gated sodium channels. And these are very sensitive and can be opened by a modestly strong graded potential. So that if we have enough stimulation on the cell body of a neuron such that we get some graded potentials, which again are due to sodium ions coming into the cytoplasm, this will cause enough local depolarization in this axon hillock region that we will all of a sudden open up a large number of those sodium-gated voltage channels. And as those channels are opened up, we will have a large number of sodium ions with a positive charge that will come into the axon, and these will cause rapid depolarization, which is measured as the upshoot of the action potential. As those positively charged sodium ions come in, we see that there is a complete inversion of the potential across the membrane. It becomes positively charged on the inside of the membrane and negatively charged on the outside. And this is known as the trigger zone. This will start or generate our action potential. As the action potential begins in this region of the axon hillock, we see that it begins to be propagated away from the hillock down towards the end of the axon, or towards the synaptic end or the synaptic knob. And this propagation of the signal is due to local current. If we generate a current in a wire or in an axon, we will find that the electrical potential will move, down that wire or down this axon. And we see the positive charge moving away from this original active region, towards the end of the axon. And as it does, it opens up voltage-gated sodium ions downstream. Now, why doesn't it open up voltage-gated channels upstream? Well, for a couple of reasons. One is that there are fewer of them upstream, and the other reason is because once we stimulate a certain region or a certain area of an axon, right after it is stimulated, it goes into a phase that is known as the refractory phase. And by definition, refractory means a period of time where the axon cannot be re-stimulated to generate a next or a subsequent action potential. Now, what this does is this puts a minimum time between the frequency of action potentials. About the maximum frequency that we can have is one generated in a certain area about every 4 to 5 milliseconds, or every 4 to 5 thousandths of a second. Now, there are two phases of this refractory period. One is called the relative phase, and one is called the absolute phase. Let's first speak of the absolute phase because the axon is in this phase first in its time of propagation. Once we open up a voltage-gated sodium channel, it will close very quickly because there's an inactivation gate. So there's two gates in these channels. The first one opens in response to the depolarization of the graded potential. And then, in a time delay of about a millisecond, we have a second gate, which is called an inactivation gate, that will close. And when this closes, no more sodium ions can come through that channel. Even if there's another strong graded potential that will come along and open up the activation gate, the deactivation gate is still closed. So we cannot get an action potential during that absolute refractory period. And that's a period of time of about 2 to 3 milliseconds that those inactivation gates stay closed. Now there's another little time delay after those inactivation gates reopen where we have a refractory period that is called the relative refractory period. And this is during a time where we have the potassium channels that are still open. It is the potassium channels that open up that repolarize the membrane. And again, they open slower than the original sodium-gated channels. Again, they are delayed by about 1,000th of a second or a millisecond. And so the relative refractory period is where we see the potassium ions that are still going from inside of the axon to the extracellular fluid. And there's a gradient to move these potassium ions out, again, because there's a high concentration of potassium ions in the cytoplasm of the axon and a much lower concentration outside. And then obviously, as we can see here, there's also a negative charge on the outside of the membrane until we get a substantial amount of potassium that leaves. And so since we have this negative charge on the outside of the membrane, potassium will be moved out. Once we get a significant amount of potassium that moves out, those channels close, and then we're back into an inactive phase of the axon membrane where it can be stimulated to generate another action potential. But as we move on, we can follow the movement of the local current down the axon, and we see these positively charged sodium ions are moving down towards the end of the axon, towards the synaptic cleft, and as they do, they are subsequently stimulating other regions downstream that become active, and then we see the refractory period in the pink region that follows these active regions.